To begin today's notes, start by taking a look at this introduction problem. Right? So when selecting from a population of all U.S. adult males, what do you think is more likely? Right? And then explain by writing at least 3 lines. So do you think it's more likely to randomly select one U.S. adult male that is 6 feet 6 inches tall? Or do you think it's more likely to randomly select 10 U.S. adult males that have a mean height of 6 feet 6 inches tall? All right, so pause the video, answer that question, and then restart it to check your answer. All right, if we look at each situation here individually, that we have one U.S. adult male taller than 6 feet 6 inches, or we have 10 U.S. adult males whose mean, using X bar, is greater than 6 feet 6 inches. All right, so if we're looking at just the distribution, right, we know from before that the mean is about 69 inches, standard deviation about 3 inches. So here's our mean. Right? And we know that 6 feet 6 inches is taller than the mean. So that would be, I'm just going to draw it in up here somewhere. Right? Now with the sampling distribution, we know we take the standard deviation of the population, whatever the standard deviation over here for the population is, and we divide it by the square root of 10. We divide it by the square root of the sample size to get the standard error. So whatever that would be, this distribution is narrower. We know the mean is the same. Right? The mean would still be about 69. But now, taking the same distance here between the mean and our data value, right, taking the mean and the data value, looks about there. Right? Much less area to the right is left in our sampling distribution, whereas area to our right is much greater. So it's more likely to have one single U.S. adult male taller than 6 feet 6 inches than to have a sample of 10 have a mean taller than 6 feet 6 inches. So today we're going to look specifically at those probabilities and how to find them. All right, so going on to the next slide then, this formula should look fairly familiar. Right? So we are now connecting probability with the central limit theorem that we looked at in the last notes. All right? We can find the probability that a sample mean, the notation for that is X bar, will fall in a given interval in a similar way that we found the probability that a random variable X will fall in a given interval of population values. So to transform the sample mean, X bar, to a z-score, we use the following formula. Right? And if you think back to our old z-score formula, X minus mu divided by standard deviation, right? Our data value, X, is now X bar, right? Because the sampling distribution uses sample means. It's the collection of sample means rather than individual values. Now the mean of our population, mu, is also the mean of our sampling distribution. This little X sub bar, or mu sub X bar, is our notation for the mean of the sampling distribution, and we know that they are the same due to the central limit theorem. And finally, our standard deviation that we used to divide by now becomes standard error, and we know they are not exactly the same. The standard error is equal to the population standard deviation divided by the square root of the sample sizes that we are taking. So in our new formula over here, we just substitute this in for the standard error, and we use X bar minus mu. Okay. So other than recognizing that the problem deals with a sampling distribution and using a different formula, the calculations will all be the same. Right? Now, going with the z-score on the calculator, we used to use the normal CDF function, and we would put in our minimum data value, comma, our maximum value, data value. I'm going to need to erase a little bit here to make more room. Right. Then we would enter the mean and the standard deviation. Right. This was for the normal distribution. Right. Now with a sampling distribution, we still have to use the same function. There's no separate function for sampling distributions. But instead of data values, we now have the sample mean. So the sample mean minimum and the maximum sample mean we're looking at. Right? We still have the same mean. Right? I could put the little x bar here, but it's the same thanks to the central limit theorem. And we don't have standard deviation anymore. We now have the standard error. But typically that's not given to us in the problem. Typically standard deviation is given to us. So I'm going to put standard deviation divided by square root of n. And you can just enter that division into this part of the function on the calculator, and the calculator will do that math for us and give us the probability just as it did with the normal distribution. All right, so let's see how this formula works in a couple problems. All right, so the SAT scores are normally distributed with a mean of 1518 and a standard deviation of 325. So if approximately 250 students from our high school take the test each year, find the probability that their mean is greater than 1600. Keyword here is mean. In all of the problems before, we were looking at a specific data value. When we are specifically asked to find the probability that a mean is something, we know we're using our sampling distribution formulas instead of just the regular z-score formulas. Alright, so let me just collect this information here. The mean is 1518, and we know that's going to be the same as our sampling mean. Our standard deviation is 325, and our sample is 250, and we want the probability that their mean, so we're talking about a mean, I want to use x bar here, is greater than 1600. Alright. Now, if I was going to use our new z-score formula for a sampling distribution, let's see here, convert that to z, I would do the mean, or the sample mean we're interested in, minus the population mean, or the mean of our sampling distribution, it's the same thing, divided by the standard deviation of the population, divided by the square root of 250. Right? Now on the calculator, this has to be in parentheses. Each part has to be in parentheses in order for this to be calculated correctly. That will come out to 3.99. So already that's a really high z-score. It looks very unlikely that this would happen. Using the calculator here, I would just use normal CDF 3.99 comma 10,000. Since I already have a z-score, I don't need to type in the mean and standard deviation, and this gives us 3.31 times 10 to the negative fifth, which as a decimal would look like that. Now, if I wanted to enter all of this into the calculator from the beginning, I would use normal CDF. My minimum mean I'm looking at is 1600. My maximum is the 10,000 that I enter. Our mean is 1518, and now I have to type in the standard error, which is the standard deviation divided by the square root of the sample size. Right? And if you try that in the calculator, you should see that that will equal the same number. Right? In the next example, the Boeing 757-200 extended range airliner carries 200 passengers and has doors with a height of 72 inches. So heights of men are normally distributed with a mean of 69.9 inches and a standard deviation of 3 inches. All right, so far that first sentence, or the first part of the sentence, is information. Now we have a mean and a standard deviation. All right, so if half the passengers are men, what is the probability that their mean height is less than? Mean height is less than 71 inches. Also, it says half the passengers. So if there's 200 passengers, half of that, our sample size is going to be just 100 now. There's a mean of 69.9, standard deviation of 3, and we are looking at the probability that the mean is less than 71 inches. So it looks like the probability that they'll fit through that door with an inch to spare. So we can use our function on the calculator, normal CDF, and just enter in the minimum, which is 71, the maximum, our minimum is going to be negative 10,000, since we have a less than probability this time. Our maximum is 71, the mean 69.9, and the standard error, which is 3 divided by the square root of 100. And this gives us 0.999877, which we round to 0.9999. Right, so it's very likely that the mean will fall below 71 inches. And one more problem to look at for the examples here. This time, quarters have weights that are normally distributed with a mean of 5.67 grams and standard deviation of 0.062 grams. Right, if 280 quarters are inserted into a machine, right, how many are expected to be rejected if the machine only accepts coins weighing between 5.55 and 5.79 grams? Right, so we have a mean of 5.670, a standard deviation of 0.062, and we have 280 quarters, and we want the probability that it falls between 5.550 and 5.790. Now, nowhere in here is it asking for a mean. Right? It's not asking the probability that it falls between those means. So we're just doing a regular normal distribution probability here. So I use the normal CDF. Our minimum is 5.550, maximum 5.790. The mean is 5.670, and the standard deviation is 0.062. So this gives us 0.9471. Now this is the probability that they fall between that range, so the probability that they are accepted. Right? So if we want to find the probability that a single quarter is rejected, we take 1 minus that probability, and that is 0.0529. Finally, if we want to know the number of quarters that are rejected, we multiply that by the number of quarters, and that comes out to approximately 15 quarters. So now, try the practice problems. I'll give you a hint. The next one does, actually both of them go back to sampling distributions. So you'll be using the new formulas, all right, not the old ones like on this. This is just an example to show you have to be careful and look at what exactly is being asked. All right. Then check your answers to those practice problems by going and viewing the next video.